Good evening, everybody. I'm Katherine Haxton, and I'm a chemist. And yeah, chemistry. It's one of those subjects that a lot of the slightly older people in the audience may remember from school. There may be some memories of blue stuff in dishes and pots, that kind of thing. A few funny smells, slightly scared teachers maybe. But chemistry is a really amazing subject. Fundamentally, it's the science of stuff. It's the stuff that probably kept you free from the rain this morning, kept you dry, that's the word. It's the stuff that you might go home tonight and cook your dinner on in your non-stick frying pans. It's the stuff that's probably the seats, the clothes we're wearing, all of that. It's literally everywhere. And chemists have a really, some might call it weird, interesting would be my opinion. Chemists have a really interesting way of looking at the world. We're really interested in how we make this stuff, what it can do, and how we can change it into different stuff. And we're also really interested, particularly at this time of year, and I agree with Lisa, there are some amazing Christmas jumpers going on tonight. How can chemistry help us to have a really, really good Christmas? Well, like so many Christmas adventures, we're going to follow tradition. I bet you all have lots and lots of Christmas traditions. We're going to go back in time, first of all. We're going to think about the chemistry of Christmas past. So, let's think about this. Yeah, suddenly we've all shifted to black and white, that kind of thing. But, you know, the first Christmas lecture was here. And the first Christmas lecture spent a lot of time talking about one of these, a candle. And light's really, really important at this time of year. The longest night or the shortest day, depending on your preference, is coming close. And most major world religions have some way of celebrating light around this time. And it sounds like such a simple thing, doesn't it? To light a candle. It's always a relief when I actually manage to light a candle. It makes me look like a half-decent chemist. But what's going on with that? I mean, you've got wax, but if we're going to the chemistry of Christmas past, we're probably talking about candles made of animal fat, some kind of tallow. It's starting to burn, but what's actually happening? What's the stuff of the candle doing as it burns? Well, the first thing that's happening is the wick burns, and that gets warm enough that the wax in the wick starts to melt. And that's really important because we're not actually burning the solid wax. So the wick does its job to wick. The wax melts, it flows up the wick, the heat from the candle starts to turn it into a gas. And it's the gas that starts to combust. First thing that happens in that flame is the hydrogens come off the wax, because wax is a hydrocarbon, which means it's made up of carbon and hydrogen atoms in fairly long chains. They're not going to be the longest molecules we see tonight, but they're very, very close. So that hydrogen comes off and it reacts with the oxygen in the air to form water. So far, it just sounds like a combustion reaction. But if you look really closely at a flame, and I've got a close-up of a different flame on the next slide, what you can see is that flames have different zones. At the bottom on this picture, and I'm not quite sure you'll see it on this one, you can see a blue zone. And that's where there's lots of oxygen present from the air around the candle. And that oxygen is essential for combustion. You need the oxygen to combine with that hydrogen that comes off the wax and combine with the carbon to form the products of complete combustion, which is water and carbon dioxide. And I know carbon dioxide is probably something you're all really, really familiar with because it's in the news a lot. But just above that blue region, you'll see a brown region. Now, this brown region doesn't have a lot of oxygen because all the oxygen is being stolen by that blue region at the bottom. And the brown region is where we get incomplete combustion and we start to get particles of carbon. That's where your soot and a sooty flame starts to come from. Now, if you can get that a bit hotter, you get up to the top bit of the flame, that sort of stereotypical flame shape, the yellow bit. And that's where those little particles of carbon have enough heat that they become incandescent. Such a beautiful word. Just means they give out lots and lots of light, typically stuff that makes it look yellow. And if you look really, really closely, and I'm not even sure you can see it up there on that candle, there's often a thin blue line right the way around the candle. It's called the veil. And it's what happens when the oxygen in the air reacts with those hydrocarbons. It's an area of really good combustion. Now, why does the flame go up? Well, we're here, we're on Earth, we've got gravity. But the flame goes up, which seems to be counterintuitive. But as you heat gases, they rise. So the wax becoming a gas, the carbon dioxide, the water produced, all those carbon particles, they go up by convection currents, and cold air from the room rushes in beneath them, and that's where we get the oxygen from. So we get that characteristic shape. So if that's the flame shape we get in gravity, and we're just going to digress a bit from the chemistry of Christmas past here, what would happen if we lit a candle in outer space? Let's assume we're in a space station. Ooh, got some hands. I think you were first. Yeah, absolutely spot on. Said it'll be spherical. No gravity, no up and down, which means we get this. So I've put them side by side on this slide. Now, I think you can just about see the wick in that blue picture. So it's probably not as big a flame. But the key thing to note is it's all blue, because there's no gases rising that have stolen the oxygen, or that have kept the oxygen away, from the combusting bit. The oxygen's just reaching the flame, and it's doing its thing. You're getting complete combustion, and you get this funny-looking blue flame. It's very, very, very different. So it's really, really important at this time of year that we have sparkly things and we have light. And a lot of our traditions at Christmas time have involved a good bit of chemistry. So Christmas trees became a thing in Britain either in 1800 or 1840, Queen Charlotte or Prince Albert. And they were traditional trees, cut down, and they were often lit by candles. And people wanted a better way to sort of really make the most of their candles, to get all the sparkle going. Now, before we had Christmas trees, we still had something similar to tinsel, except we used to decorate statues with it. Very festive, bit strange. But people started putting the tinsel on their trees, and the original tinsel was made of silver metal. Now, it wasn't the sort of hairy, long strands that you think of when we talk about tinsel today. It was, to be honest, it was more like tagliatelle, or some kind of noodle or pasta. Long, thin strips of silver metal that you could drape on the boughs of the, I was about to say the boughs of the statue, on the boughs of the tree or on the limbs of the statue. And that would reflect the candlelight, and it would make it look sparkly, a bit like sunlight off icicles, that kind of thing. People moved away from silver because there was a bit of a problem. Silver was really, really good at tarnishing. So, you forked out your money for your nice new Christmas decorations, decorated your tree with them, and quite quickly the silver started to blacken. But silver itself isn't the only shiny silvery metal. So quickly silver was combined with things like tin and lead to keep that silver metal strand thing down. And then we have things like Christmas baubles. Those were originally made of thin glass. Beautiful, beautiful fine glass that was blown, and then a solution of silver nitrate was poured into it. And in a beautiful chemical reaction, it can coat the inside of the bauble, silvering it, and then if you're really clever, you can get a stopper on the top and you can stop it tarnishing. So we've got a bit of a demonstration for you. Now I'm going to put my gloves on for this one because I've got a solution of silver nitrate here, and silver nitrate has the really nasty habit of turning your fingers black if you spill it on them, which, it's not the greatest look because it takes a few days for it to come off. Now, When we make baubles, well, as a chemist, I obviously make my baubles out of labware. You can see here, I've got a round bottom flask in the lab, and I've done this reaction with silver nitrate on the inside, and I've made it all silvery. Now, this reaction's a little bit stinky because it often involves solutions of ammonia, and I really don't want to make this lecture theatre smell like a farmyard. And there's the slight risk it forms things that are slightly explosive as well. We have an alternate demonstration with silver nitrate for you, though. What we've got, thanks to the science elves, is we've got some copper wire, and we've got a solution of silver nitrate here. And what we're basically going to do is we're going to plate the copper wire in silver. So I'm just going to pour it into the beaker. So we've got copper wire that's roughly star-shaped here. Now, this is one of these reactions that reminds you that one of the key attributes you need to be a chemist is patience, because the chemistry is going to take a little bit of time to do its thing. But what have we got in the beaker? Well, fortunately, we've also got some cartoons. While we're waiting for that to do away, though, let's take a look at some silver baubles from about the 1950s. So these are made of glass that's been blown into molds. So you can see you've got one sort of front and back views of one that looks like a little house. So the glass will have been blown into the mold, the silver solution will have been put inside it, and then it'll have been painted afterwards with little trees and little windows and details. The other one basically looks like half an orange. And it's got coloured patterns inside, and again, it's been silvered and then painted. So those baubles are from about the 1950s, or at least that's what Google image search tells me when I search for a picture of them. So what we're starting to see here is that the copper colour has gone. The copper colour's disappeared, and we're starting to see silver deposited on the wire. So, as chemists would say, at time equals 0, we had a beaker, we had silver ions in it, so that's the Ag+, and that was a clear, colourless solution. We're very big on very good terminology. And we added copper wire. Now think of the copper wire like oranges in the supermarket, or satsumas or clementines, whatever your preference is. You know, the way they all line up together, we call that close packing. And those copper atoms, copper's a metal, so it's got a lot of electrons holding the metal together. And what happens in this reaction is that the copper metal gives away some electrons to the silver ions, and the silver ions basically stick to the copper. You can see actually on this, if I lift it up, use my gloved hand, you can see I've almost just turned it into a snow globe there. Tiny little particles of silver are depositing. So from an orange-coloured wire and a clear colourless liquid, we've got little bits of silver metal. So what's happened there? Well, the silver metal's deposited on it, it's coated it. And I'm willing to bet that many of you in the room have jewellery that's been made by similar processes. It's quite common to deposit silver onto other metals, or, for example, rhodium or palladium onto gold to get that silvery effect. So what we're going to do is I'm going to very, very carefully set this to one side. I'll put it in this tray so I don't forget about it. And then we'll come back to that in a minute or two. What else has silver done for us in terms of Christmas? Well, silver gives us crackers. And I know that maybe sounds like a bit of a strange one, but the person who invented crackers was pretty much doing what everybody's trying to do at this time of year. He was trying to sell stuff. Specifically, he was trying to sell sweeties, little bonbons, and it was probably before we had all these lovely plastic wrappers that could crinkle just nicely when you opened them. And the legend, I'm pretty sure it's a legend really, was that he was dozing by the fire and he was inspired by the sound of wood burning those cracks and pops that wood burns. And I thought, wouldn't it be great if my packaging could make that noise when somebody unwraps the sweetie? Now, if you can think of it, think of the joy you have when you pop a cracker, the first one of the year. There is a bit of a wow factor to that bang, and then there's the anticipation of the toy, and then there's the groaning of the joke, all of that. So what he got was a compound called silver fulminate, which is another silver compound, and it's quite a scary one. You can detonate that with a feather. So that means that if you had a dish of it and you brushed it with a feather, it would go bang. And this Christmas, that is what is in your crackers. There's a reason you're not allowed to send crackers in the post, because they are literally explosives. And in a modern cracker, what you have is you have the two bits of the pool. They're sandwiched together like this. On the bottom one, perhaps you have sandpaper, so a bit like the edge of a matchbox. Then you have a thin layer of silver fulminate, and they're usually bound together with a simple bit of paper. And then when you pull them, the friction from the sandpaper detonates the silver fulminate, and you get the crack. So it is literally chemistry that's putting the crack in your Christmas. So, silver's been really, really important in the chemistry of Christmas past, but enough talk of the past. Let's move into the present. So a lot's changed since we were lighting candles and putting them on our Christmas tree. We're perhaps more safety conscious, or perhaps it was just that the first artificial Christmas trees were made of paper that had been coated with aluminium, and that has a tendency to catch fire if you put it near naked flames like candles. But think of everything that's changed since back when in the 19th century, when we were putting candles and little bits of precious metals on our Christmas tree. Plastics have changed the world. Think how many things this Christmas are to do with plastic. But we still have the same types of decorations. We still have decorations that are about bringing light and sparkle into the darkest time. Now, like all good chemists, I like a good experiment. And one of the things that sort of preoccupies me at this time of year is how I'm going to light my Christmas tree. Now, we looked at a candle, and back when we were putting candles on our Christmas tree, electricity wasn't yet a thing, became a thing. And electricity initially was coal and natural gas. It still is, particularly on a very cold day. But we started to get into things like biorenewable sources and renewable energy, so solar and wind, a bit of nuclear and things as well. The question is, could we use Christmas dinner to light our Christmas tree? These are the sort of things I stand and think about some days. So what I've got here is I have got a series of potatoes. Now, extensive experimentation has gone into this. We managed to establish that Brussels sprouts are not fit for purpose. Interpret that as you will. We worked out that turkey, chicken, duck, goose, tofu, and nut roast, also not that great at this. It was the humble spud. So I've got a very thin wire here. Just going to try and untangle it for you all. I've got some LED fairy lights. And this is one of the clearest ways in which Christmas has sort of modernized. We now just stick a strand of fairy lights on our tree, or perhaps we have a tree that's got them built in. And there's a whole lot of chemistry in there. So I've got our lights there. And what I've got set up here is basically a potato battery. Now, you might be familiar with this from lemons and things like that. So I've got some copper nails and some zinc nails. And we've double-checked it. We've made sure that the copper is going to the zinc and so on. So we think we've got the science right. And with a little bit of luck, it should literally be lighting our fairy lights. Could we possibly dim the lights, please? Thank you. There's always a moment, isn't there, when you realize that things aren't working. It might be that you've forgotten to turn the oven on, or maybe you've forgot the chipolatas and the little pigs in blankets, sorry. In this case, there is a vital ingredient missing. Christmas dinner needs cranberry sauce. There we go. So there we go, got the magic ingredient for Christmas right there. Chemistry has said so. And you should be able to see that far better now. The missing ingredient is cranberry sauce. Now I suspect that cranberry sauce could be a bit of a divisive issue. I think we might have the gravy aficionados and maybe the bread sauce people in the room as well, but for me it's all about the cranberry sauce. So what's actually going on here? Well, we've got a potato and we've got about 1.5 kilos of potatoes on the desk here, standard bag. Some of them are cut in half because we needed to make more of these little electrochemical cells. We've got a copper nail and a zinc nail. So at the zinc side, the zinc is giving up electrons. Now that's maybe a bit confusing because we've already talked about copper giving up electrons to silver. Well, zinc will give up electrons to copper, except it's not the copper. So the zinc's giving up electrons, and we need electrons to flow around this circuit for us to have a charge and for us to produce enough voltage and current to light our fairy lights. Now, full disclosure, I went for low energy LED lights. You've got to be sustainable about this kind of thing. I figure I can have more sets of light if they're low energy. That's my logic. So we've got the zinc giving up electrons, flowing around the circuit, then the electrons come back in at the copper, and at that point another chemical reaction takes place. It's not with the copper metal, it's with hydrogen ions in the potatoes. Because your potatoes are a little bit acidic. Not in a scary way, but they've got a little bit of phosphoric acid, and that's what makes them an electrolyte that can conduct electricity, and we can turn those hydrogen ions either into hydrogen gas or water, depending how much oxygen we've got. So we can leave this running, and one thing you will note actually is we're using a set of coloured fairy lights here. They've got coloured LEDs, and some are brighter than others. And that's because the way LEDs work, they require slightly different voltages to get them to light properly. So I reckon we probably needed a second jar of cranberry sauce, but that may really, really have been pushing it. So, do you think potato batteries for the Christmas tree are going to catch on? Yeah, I reckon so as well, you know. Because I honestly think everybody could hang their spuds off the tree, save a fortune in the baubles, and then it could self-power. It's absolutely not going to get stinky after 2 weeks in a warm house at all. But all joking aside, battery science is really, really important at the moment. We need bigger, better batteries. We need to make them out of things maybe a bit more chemically sophisticated than potatoes. But we will eventually get there. And, you know, cranberry sauce is always important. So what else have we got when it comes to the chemistry of Christmas present? What else do we have for sparkle? Well, I almost didn't finish the story about the cracker makers. After the success of crackers, the original inventor's 3 sons took over the business, and they went in search of new things to add to crackers. Mottos, gifts from around the world, little plastic toys, that kind of thing. And they eventually turned into the crackers that we have today. You're probably familiar with them. The crackers are the things that give you the little plastic toys that you still find in some drawer in the kitchen, probably, in about November. And it's only about then that you sort of decide to get rid of them. But we've replaced so much of Christmas with plastic. So candles have been converted to plastic fairy lights with LEDs, or we've gone through a bit of a phase with bulbs. That precious metal tinsel that had already changed into something with lead and tin has become shiny plastics. Now, I know we can get biodegradable versions of glitter now, but still. And baubles themselves have changed. So instead of glass baubles, which were very, very fragile, and there's a whole ton of heartbreak there when your precious bauble smashes, they've moved to thin plastics like polycarbonate, so they're that little bit more robust, that little bit more reassurance for those of us who have cats who like to attack Christmas trees. And I've got some photos of current baubles, and they've been designed really, really well. They keep the same shape, but the decorations have become more and more elaborate. And then you can see some tinsel down the bottom there. Now, tinsel also went through a phase of being made of aluminized paper, and it was also quite horrifically flammable for a good amount of time. Fortunately, it's quite flame resistant now. So what other ways do we have in which chemistry could help us have a better Christmas? Well, it's been raining all morning, and I bet there's quite a few people in the audience are a bit disappointed that that rain wasn't actually snow. Just enough snow, of the right kind, that doesn't stop the railway, doesn't stop the roads, and everybody can still go about their business. Well, there used to be a phrase called better living through chemistry, and chemistry definitely has the answer to that one. So what I've got here is I've got some fake snow. Now, there's different kinds of fake snow. If you're going to a ski resort, the chances are they're making snow by freezing water and spraying it out onto the slopes. So the original biodegradable snow, exactly like the stuff that falls from the sky, just artificially manufactured. But there's a lot of toys around at this time of year that are instant snow powder. So sprinkle a good amount in the dish, and in chemist speak, it is a granular white powder. Now, we wouldn't call that colourless, we'd have to specify it's white. What happens with fake snow? Well, you just add water. Now, as with all snow, the trick is just the right amount of water. You don't want to make fake slush. Okay. Now, it's really starting to get going now. Now, this is a chemical substance that the vast majority of people in the room have encountered before. Now, one of the weird things about fake snow is it's room temperature. It's not frozen, as in frozen water. If you put your hand in it, which I don't recommend because you'll be flicking the little white bits off your hands forevermore, it's room temperature. But the bit that's doing the fake snowness of it is a superabsorbent polymer. And it's the same superabsorbent polymer that has in the past been used in ice cream and also in nappies. And you sort of see why, because it's taken a good amount of water. Let's see if we can do a bit more. And it's locked it away. It's almost like the adverts on the TV. So superabsorbent polymer is an incredibly long molecule. In this case, it's sodium polyacrylate. And that means it's got loads of negatively charged groups that can bind to the water, and it can soak it up, and it basically just expands. It's like the chemist's equivalent of a sponge. So you got your sodium polyacrylate, you add the water, and it goes, and it gets bigger. It's in a lot of toys at the moment as well. There's lots of little sodium polyacrylate balls and things that you can get. Now, I know somebody's probably hoping that I'm just going to pour the rest of the water in. Well, so you can go too far with this. If you add too much water, You go beyond how much water the individual polymer grains can actually hold, and yeah, that's the point where it turns to slush and it gets a bit gross. But this is quite an impressive amount. So maybe you have some fake snow at home this Christmas, maybe you're decorating it, and I guess I'm going to put my sustainability hat on and say, you can actually reuse it. If you leave it to dry out somewhere, it'll rehydrate again just as well next year. The water will evaporate from the polymer strands and the granules will become solid again. Please do not do this with nappies. Okay, so what we could do is we could just take a quick look again at this copper one. And what you can maybe see now, and I'm not going to try and pull it out, you can see something else has happened. Remember I said it was a clear, colourless solution to begin with, and we put the orange copper metal in, then the copper metal turned silvery. Well, what you can just about see is the solution is now blue. So my slides were incomplete. I missed off a really important bit. And that was the point where the copper had lost enough electrons to become copper 2+ ions, and they dissolved in the water. And copper 2+ ions give you that beautiful blue colour. It's very similar to the copper sulfate solid that many of you will have memories of from chemistry. But the clear colourless silver ions have become silver metal, and the orange copper metal has become blue copper ions in solution. Absolutely beautiful. I didn't actually expect to see that it would go blue quite so vividly, but that's an absolutely beautiful result. So, metal plating, chemistry, fake snow, lots of science in here. But there's another use for that superabsorbent polymer. It used to be used for diapers for astronauts. I know. It's a very, very random one. But if you're on a long space mission, then it's pretty important to be able to go to the toilet in comfort without taking your spacesuit off. So when it comes to things like the chemistry of Christmas future, I start wondering, I look around this audience and I wonder if we've got any future astronauts in here. Anyone interested in being an astronaut? Yeah, okay, anybody interested in being a scientist? Okay, you can be both. Anyone interested in being an artist? Yay, okay. Now, we're going to go to Mars. There's going to be a whole ton of really great science involved with going to Mars, but there's going to be a whole load of really great scientists and artists and astronauts that are going to be on a spaceship for up to 7 or 8 months, maybe a bit longer, and they're going to need to celebrate Christmas. Now, how are they going to do that? Well, I'm guessing that they're going to have to find things in the lab to make their Christmas tree out of. Or in this case, a chemistry. Yeah, thank you. I know, right? But this is an absolutely brilliant example of the class of chemistries. You can see we've got benzene at the top of it. I've got all these beautiful things, and thank you to Rosie for making it. I'll give you some of those. But if we're on a spaceship and we want to bring sparkle, the chances are we won't have brought potatoes and we won't have brought LEDs. So we're going to have to break open the chemiluminescent sticks. Now, these would be useful to have if we're going on a long space journey because they don't require... You may want to give it a bit more of a bend and a crackle to get it to really light. So these are the ones that are supposed to be made into bangles. And if we're getting to the stage where we're having Christmas on our way to Mars, there's nothing like throwing things into the audience to lose your train of thought. Then we might start to make our Christmas decorations out of something like this. Now, these are really common in emergency kits. A bit of chemiluminescence, which is an interesting set of chemical processes. And what you'll see, they're not quite glowing yet, but you can see that they're already coloured. Not very strongly, not very effectively, but they've got a bit of colour on them. Now, I reckon that there's going to be quite a lot of scientists don't mind making chemistries and don't mind making these. But what's actually going on in terms of the chemistry of these things? So, what you might have heard as we were snapping these is you might have heard some crackles. And these are made up of a plastic tube, and inside it is a thin, thin glass tube. And that's to keep the chemicals apart so they don't react until you're actually ready for them to start doing their thing. Now you can see up on the slide that I've drawn some molecules. So there's a big molecule in there that I've coloured 2 bits in a sort of creamy coloured. That's the molecule that's just in the plastic tube, and it's also mixed up with dyes of different colours. So far, it's just a mixture of chemicals. The glass tube is filled with hydrogen peroxide and a couple of other chemicals as well. And when you mix them, the hydrogen peroxide starts to basically obliterate that big molecule. You might be familiar with hydrogen peroxide from hair bleach, disinfectants, contact lens cleaning solutions, that kind of thing. So at stronger concentrations, it can really do some pretty amazing stuff. So the hydrogen peroxide pulls the molecule apart. The bits that I've coloured in the cream boxes, that's it. They were only there to protect that middle bit of the molecule. And it forms a really highly reactive intermediate. And you know what? We're not actually entirely sure of the structure of that intermediate. I've drawn it up there as a square shape with almost like 2 oxygens as bunny ears and 2 oxygens down below. But we're not 100% sure because we haven't been able to catch it. We haven't been able to use some of the techniques that chemists use to analyze stuff to see what it actually is. But what we do know is it's got a lot of energy for a little molecule, and it transfers that energy to the dyes in these light sticks, and that causes them to glow in a process called chemiluminescence. So chemical energy caused by a molecule falling apart is transformed into light energy that we can see, and it makes the dyes glow. Now, obviously, the thing that's missing from our chemistry is the lights. Now, hydrogen peroxide up there is a pretty interesting molecule. Those of you who are on the ball this, still Tuesday, right? Tuesday evening, will notice that hydrogen peroxide is like water, but with an extra oxygen. And that's going to be a really big key feature, because we've actually jumped ahead a little bit in our trip to Mars. I'm talking about the journey. How do we actually get up there? Now, if we're going to get up there, what we're going to need to have is we're going to have some rockets. And a rocket, original rocket, is basically a big candle, except there's a few problems. It's a candle that's got to burn against gravity, because we want the hot gases to go down, not up, so the rocket goes up, not down. And it's going up into Earth's atmosphere, and the problem in Earth's atmosphere is that the oxygen starts to run out the higher we go. So we're going to have to take our own oxygen with us. Now, there's some forms of rocket fuel use kerosene. So kerosene, a bit like petrol. Unlike wax, it's not a solid at room temperature, it's a liquid, but it's still a hydrocarbon. So really, those kind of rocket blends are literally gigantic liquid candles. But to do that, what you have to have is you have to have some liquid oxygen. And we've got some here for you today. We've got the science elves to demonstrate. And we have another contentious Christmas dinner ingredient. We have a Yorkshire pudding. So I don't know whether that features on your Christmas table or not. Now, the liquid oxygen has been made for us specially today. It's not something we normally keep around. So what I want you to do in proper rocket fashion is I want you to start a countdown. 3, 2, 1. Third time's the charm. Can you give the science elves a round of applause, please? So liquid oxygen, and you can tell by the fact that we've suddenly brought the safety shields out and that, is quite a scary compound. Well, quite a scary element. Oxygen, we know, is an oxidant. It's the origin of the term. We know it's a necessary ingredient when things burn, when they combust. You have to have a fuel, you have to have a source of ignition, and you have to have a source of oxygen. So when we lit the candle, the ignition was the match, we had the fuel in the wax, and then we had the oxygen in the air. This time we used a burning splint to light the liquid oxygen, and the fuel was the Yorkshire pudding. The Yorkshire pudding did not stand a chance. Liquid oxygen, although you couldn't have seen it there, is also a very, very beautiful pale blue colour. Now, can anyone tell me how cold liquid oxygen is? I think your hand was up quick. Ooh, not that cold. But you're in the right region. It's not minus 200. You're going to have to shout, though. Yeah. Yeah. Ooh, it's colder than that. In the white hoodie. Minus 100. That's very precise, but it's not cold enough. It's about minus 182. Now, that's really, really cold. But it's not as cold as liquid nitrogen. Now, I'm going to put my gloves on for this because liquid nitrogen is cold enough, as liquid oxygen is, it's cold enough to burn me. And I really, really do not want burns. I didn't want my fingers turning black with a silver nitrate. I don't want liquid nitrogen burns either. Anyone want to guess how cold liquid nitrogen is? Minus 900 odd. We can't get things that cold. We're not allowed. The universe has other ideas. It's close to minus 200. It's minus 196. And I can tell from all the eager hands up in the room that lots of you had some great answers to that. So liquid nitrogen is what we use to form liquid oxygen. So minus 196. Now what you can see is when I pour it into that pot, it's literally boiling. From the perspective of the liquid nitrogen at minus 196, that glass is absolutely boiling hot. Now, other than to make liquid oxygen, why would we be playing with liquid nitrogen? Well, there's a really, really important thing we've overlooked in discussing going to Mars. How on earth is Santa, well, not how on earth, how on Mars is Santa going to get there? Because, you know, we've got the whole thing worked out for getting around the Earth very, very quickly, but, you know, interplanetary travel, and having a spacesuit that can stand the cold temperatures. And this is another region where materials chemistry kind of comes into its own. So I have a sample of various materials that Santa may or may not be taking to Mars. So let's put some things in. Firstly, I have sprouts. I'm going to use the really long tongs. Now again, from the perspective of the liquid nitrogen, the sprout is boiling, boiling hot. Now you need to have at least 3 sprouts on Christmas Day. That's the rule, right? Or is that just something somebody told me? So we're going to leave them until they stop boiling. Once the nitrogen stops boiling on the sprouts, then we know the sprouts are done. Again, that's the rule of cooking sprouts, right? Now what I've got here is I've got some rubber tubing. Now rubber, flexible natural polymer, you can see it's beautifully flexible here. I'm going to put it in here, and I'm very carefully aiming the hose end of it away from me, and safety shield stopping it from going out to any of you. Again, it's boiling hot from the perspective of the liquid nitrogen. Now rubber behaves like a lot of polymers do. When you cool them down, they go from that beautiful flexible state into something quite different. So if we take it out, instead of it being flexible, and I can literally shatter bits off it just by bashing it hard enough. So we better hope that Santa doesn't have rubber boots on. Could be a bit of a problem. Now, let's see how my sprouts are doing. They're bubbling away merrily. I think that's possibly one of the most satisfying sounds I've ever heard. So what's happened to the sprouts? So we know that the polymer in the rubber, it's frozen, it's become brittle. In the case of the sprouts, it's the deep freeze for the water that's in the cells in the sprout. So biological material freezes and then it becomes very, very fragile. Now, what else have I got? Should we try some tinsel? Now, this is one of these ones where I literally have no idea what's about to happen next. Because who honestly would take a beautiful piece of tinsel and freeze it? Now, again, the tinsel is very, very hot compared to the liquid nitrogen, but it's not boiling as much. Okay, what I think we'll do is if I pour a little bit more of the liquid nitrogen in there, we'll leave it to see what happens over time. Because it's gone a bit crunchy, but it hasn't done anything else yet. And I think it's quite possible that Santa might wear tinsel-y things on a trip to Mars. Okay. Let's face it, people, it's the cocktail of your dreams right there. Okay. Okay, so I've got a Christmas stocking in there. So that's probably made of another kind of polymer. And probably acrylic, similar to the sodium polyacrylate. It's a very, very different result. Pulling it out there, it feels almost like it's wet. It cools down very, very quickly. Then the liquid nitrogen is literally dripping off it. But otherwise, it's not really that changed. That's probably a pretty good result for Santa. Some winter woolies. But is it my imagination, or is the colour a little different? Let's see what happens when it warms up. Right, let's see what our tinsel's done. Yep. That's stayed pretty well intact as well. So I think we've got two options for Santa's suit here. It's got to be knitted acrylic wool, and then we've got to have some tinsel on it. Right. Last couple of things that we'll try. Because we haven't tortured them enough today, we shall try a Yorkshire pudding. Okay, and watch the rows carefully. So, is a rose going to be more like a Brussels sprout, or more like a knitted stocking or sock? Yep. There we go. So what we can see is the chemistry of stuff, the chemistry of materials, changes greatly depending on temperature. So we go from having, well, beautiful roses to having slightly mangled roses. Tinsel doesn't really do much. And maybe that's a bit of a thing with tinsel because of how it's made, it doesn't really do much generally. It pretty much just stays in this form for a very long time. Yorkshire puddings, keep them in the deep freeze too long and they're probably not going to look like Yorkshire puddings anymore. And sprouts, well, the liquid nitrogen really says the sprouts just have to go. So one last thing. You might have noticed, particularly when I pulled the stocking out, that the liquid nitrogen was flowing off it. And if I pour some out here, you can see little beads of it skirting about on the desk. And the liquid nitrogen itself isn't really touching the wood. The wood is too hot for it. So the liquid nitrogen, the little droplets of it, they're zooming around on a cushion of nitrogen gas. It's almost like it creates its own hovercraft, and it can go zooming around. And it's simply because something so cold poured onto something so warm, and I don't necessarily think of a wooden tabletop in a room temperature room as being hugely warm, but there you go. So it's another interesting property of something like liquid nitrogen. So, we've covered a lot of ground. We've gone back to the chemistry of Christmas past. We've talked about candles and how they burn. And then we zoomed into the future and thought about rocket fuel and liquid oxygen. We've talked about sparkle and how it started out as silver metal and how we could make silver on deposit onto the inside of vessels, like thin glass baubles and things like that. And then we've talked about different kinds of chemiluminescence and that sort of thing. And we finished up with really mangling a whole load of Brussels sprouts, innocent Brussels sprouts, I might add, in liquid nitrogen, but exploring some of the strange properties of that. So, I think at this point, we probably have some time for some questions if anybody would like to ask something.